Alright, we're on to part 2 here, so we're going to keep on going. And let's see where we start from. Current slide, please. Good, and so we talked about our nucleides. Go on from here. We have the neutron to proton ratio determines the stability of the nucleus. This is very true. For low atomic numbers, equal numbers of protons and neutrons, stable. Above the atomic number 20, more neutrons than protons usually means more stability. And so stability is very good. Like I talked about earlier, last thing you want is some type of random reaction going on in your chemistry experiment or whatever you're looking at, especially when you're dealing with very, very powerful nuclear substances or radioactive substances. Radiation is not something to be played around with. Now, right here it says nuclei whose neutron to proton ratio is unstable undergo radioactive decay by emitting one or more particles and or electromagnetic rays. This is very important. Please make sure you get this concept down because this is a huge, gigantic part of our class and what we're going to be doing. So right here we have heavy, unstable element. So for this example, they used uranium. And you can see here, spontaneous decay. And that's one of the things that makes uranium such a big deal. It just spontaneously decides, you know what, I'm going to break off into these different things. Now, we'll be able to tell through something called a half-life, we'll get into later, that you can predict how quickly the uranium will turn into lead, because that's just what uranium tends to turn into through different types of decay. However, it still is pretty unpredictable. You don't really want to be messing with this stuff without a proper suit. So you have our alpha particle. This bounces off sometimes during spontaneous decay. Sometimes you get a gamma ray, which is extremely dangerous. And then sometimes you get a beta particle, and you get a neutron, you get a proton just being, randomly shoved off depending on what type of decay is going on. Oftentimes, all three are going on at once, just like that experiment we saw with Ernest Rutherford earlier, and he was able to see all three of them in his example. He probably used something like uranium. Now, this is the chart, and this is where we're probably going to end for today, because this chart, even though it is very, very important, you can see it has a good amount of stuff here. So, listen up. It says nuclei whose neutron to proton ratio is unstable undergo radioactive decay by emitting one or more particles and or electromagnetic rays. Now, the reason it does this is because it wants to become stable. In this nuclei's life, the only thing it wants is just some stability. It's just, I just want to calm down, I just want to relax. And so he's going to go through one of these changes. So let's look through them here. He can go through an alpha decay, an alpha decay, and when alpha decay happens, it actually gives off a helium nucleus. And so I talked to you guys before about why helium is such a rare thing and why a lot of places pay so much money for it. It has to do with, it comes from, in a lot of cases, radiation. The mass is 4.0026 AMU, or atomic mass units. It has a +2 charge, and the penetration of this alpha decay is very low, or alpha particle is very low. It's not really going through much. I believe you can even block it with a piece of paper. Now, beta decay is a bit more serious, and it's very interesting what beta decay does. Now, notice this symbol here, and it gives off a beta particle. And it is basically an electron in this sense that just randomly burst forth from the nucleus, which is really strange and makes a lot of people wonder about a lot of different things. Beta decay is one of those things I don't really even truly get, and you have to really go into some serious nuclear chemistry as to how this works. But has a very, 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 very small mass. You see that number there? It's pretty darn small. And then its charge is -1. So actually, when this thing comes out of the nucleus, it gains charge, which is just kind of crazy to me. And then from there, it's got a low to medium penetration, so it could probably get through a piece of paper or get blocked off by your skin. Now, gamma is very, very, very dangerous. First thing we notice here, it's got like 0, 0, and so it's basically just an energy wave coming out of the nucleus of this element that is extremely unstable. High energy radiation. High energy. Very serious here. This is what causes a lot of the damage. Mass is 0. We can't, like, there is no mass to it basically. It's just energy. Charge is 0. And it has a high penetration. This is why you need lead-lined suits to deal with a lot of radiation. Gamma rays will literally go through your body and give you small perforations in different organs, causing issues, or mess with your actual DNA. So gamma radiation is a serious problem. Gamma radiation is what is responsible for the majority of Madame Curie's illness and other things along with that. Seeing as she was the real one to discover that it was very dangerous, it was a pretty big deal. Now, proton emission happens sometimes, and you will get a proton that will randomly just spit out of your nucleus to try and make it more stable, and you get a random hydrogen nucleus just getting spat out. Its mass is, it's pretty low, but write that down. Make sure you write this table down. It's very important once again. It's got a charge of +1, and then it's got a low to medium penetration. So it's similar to your beta in that sense. You can see a lot of similarities between the charge and the penetration of the beta and the proton. And then finally a neutron identity right here. A neutron pops out of your nucleus here. It's a bit heavier than your proton, and its charge is 0 because neutrons are neutral. Neutron, neutral. And then finally, its penetration is very high, and so when a neutron gets blasted out in a actual radiation context, it's a pretty big deal as well. So you want to be watchful for that. And so I think that is where I'm going to end this for today. Thank you very much for listening. Make sure to go to Google Classroom so you can actually see the assignment and the questions I want you to answer. Thank you very much for your time, and goodbye.